So in the third section of our class, we're going to be focusing on the atmosphere and what's probably the biggest hazard that we're dealing with in our society today and moving into the future, which is climate change, a phenomenon of the atmosphere. So in this first lecture for the third section of our class, we are first going to understand the composition and structure of the atmosphere, right? What is this portion of the Earth system? How does it work? And then look at how human activity has changed the atmosphere. So we'll begin with a diagram giving us a cross-section through the atmosphere. Okay, so we've got our solid Earth that we learned about, and then we took a cross-section through in an earlier lesson to understand the different layers that that was made out of. And now we're looking at the atmosphere, this thin envelope of air, thin envelope of gas that surrounds the solid Earth. And just like the solid Earth is made up of those layers, the atmosphere is made up of layers. Starting from ground level, we have the troposphere, the stratosphere, the mesosphere, and the thermosphere. And an important thing to understand about the atmosphere is that the density of the air varies a huge amount between the different layers. The air is far more dense at the surface of the Earth than it is as you go up. And in fact, this diagram here cuts off at about 100 kilometers above the Earth's surface. That's not the outer edge of the thermosphere. There is no really well-defined or non-arbitrary outer edge of the thermosphere, because the atmosphere just gets thinner and thinner and thinner as you go up until there's sort of practically nothing left. But there's not a neat boundary the way that the surface of the solid Earth provides this really neat and clear boundary. And in fact, this lessening of density as you go up is so significant that about 3/4 of the mass of the air, so you can think of sort of 3/4 of all the air molecules and the weight of them that we've got, is located in the troposphere. So the troposphere is where most of the action occurs, and that's the layer that we're really going to be interested in for the rest of this section of our class. So we want to be aware that there are these additional layers above the troposphere, and there are some interesting things go on up there. So for example, the ozone layer is up there. We're not going to have a chance to talk much about the ozone layer and the thinning of it. That's been a significant environmental issue and so forth. We're really going to be focusing on the troposphere, which, as you can see there, is high enough to go up past the tops of our tallest mountains. So the top of Mount Everest is still in the troposphere. The height at which you would fly in a commercial jet is still in the troposphere. So the vast majority of us are going to live our entire lives in the troposphere. So unless you join the Air Force and are on some top secret missions flying really high up in specialized planes, or you become an astronaut and perhaps leave the atmosphere altogether, all the rest of us, we're going to live our whole lives in the troposphere. The troposphere is where all of our weather and climate are happening, and so that's the layer that we're really going to focus on. So if we look at the composition of the air in the troposphere, we've got a pie chart here. This is the composition of dry air. You'll see water vapor is not on here because, if you remember from our earlier lesson, the amount of water vapor in the air can vary wildly, right? You can go from 0% humidity up to 100% humidity, which, if the air is nice and warm, can be a pretty substantial amount of water vapor. So this is just looking at dry air, what you'd have in 0% humidity, no water vapor. What else is the air in the troposphere made out of? And you'll see that it's mostly made out of nitrogen. 78% of our air is nitrogen, and that's a fairly inert molecule. It doesn't do a whole lot, but it makes up the bulk of the air that surrounds us. And then nearly all of what's left, another about 21%, is oxygen. So we have a huge amount of oxygen in our air around us, and that 21% oxygen figure is actually really important for the existence of fire on the surface of the Earth. The Earth is the only place that we know for sure in the entire universe that can have fire. And fire requires oxygen. Fire draws in oxygen from the atmosphere around it. And in fact, if the amount of oxygen in our atmosphere were to go down to somewhere in the range of 15%, it would be incredibly difficult to keep a fire burning without supplying concentrated oxygen to it, right? You wouldn't be able to just light a candle, light a campfire, have a gas stove or anything like that. There just wouldn't be enough oxygen around. Whereas if the oxygen concentration were to go up to about 25% or so, it would be incredibly difficult to put out a fire. Once a fire got going, most of our ways to put out a fire involve smothering it, involve depriving it of that oxygen. You know, if you have one of those little candle snuffers, what that does is it deprives your candle of oxygen. That would not work very well if we had 25% oxygen. There would be too much there to keep away from the fire, and the fire would be sort of burning constantly. So we really hit the sweet spot for being able to have fire, use fire on the surface of our Earth, because our oxygen is about 21% of our atmosphere. So between those two things, you've only got about 1% left. And most of that percent is made up of argon, another very inert gas there, making up nearly 1% of the atmosphere. So all of the other gases that we're going to talk about, okay, all the other gases that we're going to be discussing in understanding the greenhouse effect and everything like that, make up a minuscule fraction of the amount of air we have. And you'll notice on the listing there, one gas that you should already be familiar with from diagramming the carbon cycle is carbon dioxide. And this particular diagram is a few years out of date. It's listing carbon dioxide as making up 0.038% of our atmosphere. It's now a little higher, more like 0.042%. Carbon dioxide makes up this tiny fraction of the air, but it's because carbon dioxide makes up such a tiny fraction of our air that human activity is able to change that substantially. Nothing people do is really going to change the percentage of our atmosphere that's made up of oxygen. There's just too much of it for us to really make a dent one way or the other, removing or adding oxygen to our atmosphere. Whereas with carbon dioxide, such a small amount to begin with that human activity can very easily add to it. And so it has gone up from about 0.02827% prior to the Industrial Revolution up to now about 0.042%. As I said, we're well on our way to doubling the amount of carbon dioxide that's in the atmosphere, which means doubling the effect that that carbon dioxide has on our world. So it's actually the fact that there's so little carbon dioxide to begin with that means that human activity can throw it out of whack so easily. So as I said, that percentage of carbon dioxide has been changing substantially over the past roughly 200 years. And our best data on this is something called the Keeling curve. So this is named for a scientist named Charles Keeling, who began recording CO2 levels at an observatory on Mauna Loa in Hawaii back in the 1950s. And so what you see here is his data up through June of 2021 about how much CO2 is in the atmosphere. And one thing that I'll note about this chart here is that there's one significant problem with this chart, and it goes to show that even NOAA and prominent universities like UC San Diego can sometimes make bad charts, because whenever you look at a chart like this, you should always pay attention to where is the zero on the vertical axis. And in this case, the zero is not on the chart. The zero is way off somewhere below the chart, right? That lowest tick mark looks like that's about 310 parts per million CO2 there. So by cutting off that bottom, this does kind of exaggerate the amount of change that happens over the course from Keeling's first observations up till the most recent data. So that's something you always want to keep in mind when you're looking at a chart. You want to pay attention, where is the zero on this chart? Have they cut off the zero and therefore kind of exaggerated the amount of change, the visual presentation of the amount of change that's happened? But in any event, once we factor that in, right, we can read this chart and not be misled by that. It's still a pretty significant increase from around a little under 320 parts per million to around 420 parts per million over the course of a little more than half a century. So you'll see two things going on in this chart. So the red line is the monthly measurements, and you'll see that it has this very regular up and down kind of zigzag to it. It's this annual cycle, and that's due to the growth and dormancy of plants. So if we think back to our discussion of the carbon cycle, we know that as plants grow, they photosynthesize, they take CO2 out of the atmosphere, they move that CO2 from the atmospheric stock into the biosphere stock. But then when plants go dormant, when they're not growing during the winter, then more CO2 is being returned to the atmosphere by decomposition, by animals breathing out. And so that creates the seasonal up and down. Now, in theory, the ups and downs should be balanced because when it's summer in the northern hemisphere, it's winter in the southern hemisphere and vice versa. However, we have a lot more land in the northern hemisphere. And so that means we have a lot more growth going on during the northern hemisphere's growing season than we have in the southern hemisphere's growing season. So the pattern in the northern hemisphere tends to dominate the overall composition of the atmosphere just because we have unequal amounts of plants in each of our hemispheres. So that's why we get this little zigzag up and down in our monthly measurements. But then if we look at the black line, which is annual measurements, so we average the whole year together to even out that annual cycle there, we see there's a clear upward trajectory. We have a clearly moving upward in our amount of CO2 in the atmosphere. So that's observational measurements, directly measuring the air starting back at the end of the 1950s. But we can push our data about CO2 in the atmosphere back even further. So here we see a chart which, again, take into consideration that this cuts off at 175 parts per million there. It doesn't go all the way down to the zero either. But we can see there's significant ups and downs in the amount of carbon dioxide in our atmosphere when we use ice core data to look back over 400,000 years. So what you've got on that chart, my face is slightly covering the label there of the current level of CO2. The little red bit at the end is the Keeling curve, which has been, compressed to fit onto this graph, so you can barely see it, sloping forward because it's over such a tiny fraction of the period of time covered by this graph. And then the blue is ice core data, and what you can see is we have this temperature fluctuation of our Earth through the ice ages that's correlated with changing CO2 concentrations, and so there's a drop that you see there just before the present that takes us to the last glacial maximum, which was about 18,000 years ago. So that's that low point, the first low point as you read over from the right-hand side of the graph. And that is quite a long time ago. Our written history in the world only begins about 5,500 years ago. So after our CO2 levels had bounced back from that last glacial maximum up into the upper 200s parts per million there. So this cycle of ice ages, right, this is going back quite a long time. Well, the other thing you can see here is that our current concentration of CO2 in the atmosphere is way above what it was in any of the past interglacial periods. So this most recent interglacial, we were in the neighborhood of 275 or so parts per million CO2. You can see that's about the same each other time that CO2 peaked. We've got 4 other peaks that we can see in this data, but now today we are way beyond that. And even way beyond, this graph, again, is a little out of date because we're now up above 400 parts per million, not was that like 385 or so that is on the chart when it was made a few years ago. So here's how we get that ice core data. Right? The Keeling curve is kind of straightforward. He had a system of glass vessels that he would use to take a sample of the air just from the air outside the observatory. But how do we go back farther than that, when nobody was taking those sort of observations. Well, nature was actually preserving samples of the atmosphere for hundreds of thousands of years, and was doing that in our large glacial ice sheets in Greenland and in Antarctica. So in these locations, each year you get some snowfall, and that snowfall forms another little layer on top of the glacier. And as it builds up, it gets compressed into ice. As that's happening, it's going to trap little bubbles of air. And there are going to be little bubbles of air in among your snowflakes that get compressed down and trapped as it turns into this glacial ice. So these are like little sample cans of past atmosphere. So if we drill down into our glacier and we remove a core, right? So we remove the cylinder like the woman is holding up there in the lower right picture, we can then cut that apart and we can remove that air from those little bubbles, and we can analyze its composition. We can see how much of different gases the air was made up of at that time, and we can also count the layers back to figure out at what point in time that layer was trapped, right? What year does this layer's ice represent? And these glacial cores go down pretty deep. We can go several miles down into the glacier to extract these cores, which allow us to reconstruct the composition of the atmosphere going back, about 500,000 years or so. So this huge change that we see when we connect the Keeling curve to the ice core data, this movement of our atmospheric carbon dioxide levels into uncharted territory, is often pointed to as a key component of what's called the Anthropocene. So the Anthropocene is defined as a geological time period characterized by humans as a dominant force shaping the Earth system. So human activity making substantial changes in how our Earth system works. That's what we're referring to when we talk about the fact that we're now living in the Anthropocene. And there is some controversy over when we should consider the Anthropocene to have started. Right? What is the starting point at which we say now humans are making this substantial alteration to how our Earth system works, above and beyond the impacts that any species has as part of the ecosystems that they're part of. So I have a chart there on the right of some possible dates that we might point to. So we can't go any farther back than about 150,000 years ago. That's when Homo sapiens, our species, evolved. Obviously, we weren't a dominant force in the Earth system prior to existing, and generally we wouldn't think that any of the earlier species that we evolved from, Homo erectus, Australopithecus, those kind of species, had the kind of influence over the Earth system that modern-day Homo sapiens have had. The first big event that's often pinned on humans as making a really substantial alteration in the Earth system is the extinction of megafauna. So on all of our different continents during the last ice age, we had a variety of very large species of animals. So here in North America, we had things like woolly mammoths, giant camels, dire wolves, giant ground sloths, a variety of very large creatures. In Australia, they had gigantic carnivorous kangaroos and wombats the size of cars and huge flightless birds. So, on each of these continents, we have these gigantic species that lived during the last ice age. And at some point after that, these species went extinct. And they went extinct at different points in time. What happened in North America wasn't the same as what happened in Australia, and so forth. And so many people have suggested that what made the difference, and what caused these extinctions to happen, the reason that these species couldn't survive in the current interglacial, even though they made it through multiple past interglacials, was the presence of human hunters. And that's still a very controversial theory. There's a lot of conflicting evidence. It may not have happened the same in all parts of the world. So, human hunting may have been an important force in some areas of the world and less so in other areas. And so there's still a lot of archaeology going on trying to pin that down, but that's kind of the first thing that some people will point to as sort of the earliest possible point at which we could point to the Anthropocene starting to kick in. Another major change happened around 8000 BCE, which was the first farming. So farming is a major shift in how people relate to our world around us, a big increase in the amount to which human activity modifies our landscapes. So the first advent of farming in the area that's now sort of Iraq, Syria, Israel, Palestine, that kind of area, was also a big change, made a significant impact on our Earth system. Around the year 1, we have pollution from Roman industry. And the Romans were producing all kinds of goods, including lots of metal-based goods that involved a lot of pollution from smelting them, emitting a lot of lead in particular. The Romans had no concept of lead as being a harmful thing, as causing lead poisoning, and so they used lead all the time. They thought it was a real useful metal to work with. And so we can detect the pollution from Roman industry in ice cores starting around the year 1. And so that's a pretty significant milestone in that we're seeing the effects of human activity in one part of the world, right, in like the Mediterranean area, being noticeable in ice cores halfway around the world in places like Greenland. Another big step was around the year 1500. So this was, just after Columbus's voyages. He brought the existence of the Americas to the attention of Europeans, and various European conquerors started to come to the Americas, and one of the results of that was a huge population crash because the Europeans brought diseases with them that killed enormous numbers of indigenous people in the Americas because they'd never been exposed to those diseases before. They hadn't evolved any immunity to them, and so they were just absolutely devastating. Things like measles, smallpox, chickenpox, influenza just tore through indigenous communities throughout the Americas. And when you lose a huge number of people like that, you also can now no longer do things like hunting and farming on the large scale that people used to. And so there was a massive regrowth of dense forests around the Americas as a result of these European introduced diseases. And that caused a big shift in our Earth system. Now you can imagine lots more trees growing that aren't being, cut down for human use or to clear fields for farming and stuff. That's going to suck a whole lot of CO2 out of the atmosphere, and that is going to shift that carbon cycle. It's often credited as a contributor, if not sole cause, to a cooling of climate that occurred in the early modern period. Around the year 1800, we have the Industrial Revolution. So we see a massive growth in the extraction of resources from the world and our ability to process them, make stuff out of them. We see the use of fossil fuels as major sources of energy with the Industrial Revolution. And so that has a very big impact on human modification of the Earth system. And then the latest date that people will point to as where they think we should consider the Anthropocene to have started is around the year 1950. So this is just after World War II, and we have what's called the Great Acceleration. So we already had, industrial society going into the war, but as a result of things like technological developments that happened during the war, this big growth of the global economy after the war, we see this sudden uptick in the rate at which people are producing synthetic chemicals, putting them into the Earth system, and causing significant alterations to how our Earth system operates. So, there's debate about which of those benchmarks to use to say this is when the Anthropocene really started. I don't know that there's much to be gained by, saying this one is the correct starting point for the Anthropocene. I think it's more useful just to understand all these different points at which the way that people modify our Earth system changed, accelerated, increased in its scope and thoroughness. Now, this name Anthropocene is a controversial one because it's based on the Greek anthropos, which just means person. So it implicitly blames just all humans, right? All of us as a species for these effects. But in fact, all of these things are the result of particular social, political, and economic systems. And it's not just a whole bunch of people doing their people thing that causes this. It's people organized in a certain way, people who work together in a certain format. And so some people propose alternative names. So instead of saying Anthropocene, we might say, for example, the Capitalocene, which puts the blame on capitalism as a specific political and economic structure that enabled humans to have a different sort of impact on the Earth system than a non-capitalist society would have. Some people propose the name Plantationocene, based on the idea that it's plantation-style resource extraction that began, in the 1400s or so, that is really responsible for the change in how humans impact our Earth system. There's also the term Cthulhucene, reference to Cthulhu from H.P. Lovecraft's mythos, with the idea that we're making things weird. We're going outside of the sort of understandable norms of the prior Earth system. So there's controversy about this name Anthropocene as well, and what it implies about who's responsible, who receives the benefits, and who receives the harms from this set of changes. And I think it's important for us not to homogenize all people and to be able to recognize the way that social, political, and economic systems are behind the impacts that we have on our Earth system. And this is a good place where you can connect what you're learning in this class about scientific understanding of the physical world and how it operates with what you're learning or have learned or will learn in your social science and humanities inquiry classes, where you learn about those social, political, economic systems and how they function for our society. So I want to really encourage you to draw the connections between the different courses you're taking in your Rock Studies program here. So to reinforce that idea that it's not simply humans collectively as a species that are having these impacts, this is a graph showing annual total CO2 emissions broken down by country and region. So we saw the overall outcome of increased CO2 emissions by humans. We can see that in the increasing amount of CO2 in our atmosphere through things like the Keeling curve. This chart shows us, well, where is that CO2 coming from? Who's producing that CO2? And one of the things that you can see there is that historically, the United States and Europe have been the two biggest contributors. Okay, so the majority of that CO2 in the atmosphere has been from the United States and Europe. These two regions started emitting in substantial amounts well before anybody else. But the other thing you'll see on this chart is that those emissions from the United States and Europe have plateaued or even decreased in recent years. And some other parts of the world, particularly China and the rest of Asia, have now been catching up, essentially, have been starting to emit much more of the world's total CO2. So at the present, if we look at just year after year emissions, China is out emitting the United States. Now, the asterisk on that, of course, is that a lot of those emissions from China are to make products that they then ship to the United States. So it's U.S. consumers that are benefiting still from a lot of those emissions. They're just now occurring within the boundaries of a different country. But it still means that the approach that we might take if we want to try to bring down these total emissions is going to be different if a lot of them are being emitted now in China, other parts of Asia, as opposed to being largely from the United States or Europe. So your lab assignment for this week is nothing. You'll be tested on the material from this lesson, but you have your test from the previous section to do this week. So there's no lab assignment for this lesson this week.